from this video, I'm gonna show you guys some properties of the integral. Some of them might seem like very obvious and easy to understand, and that's true. But the proof of them might not be that straightforward. So I'm gonna show you almost all the proof of the properties that I listed. There are 5 properties in total. So now let's get started. So the first property says that, so we first assuming that f and g, two functions, are integrable on a, b, the interval. The first property says that the function f plus g is going to be integrable on a, b as well, with the integral of f plus g from a to b is going to be equal to the integral of f from a to b plus the integral of g from a to b. And the second property says for a real number k, the function k times f is going to be integrable as well, with the integral of kf from a to b is equal to k times the integral of f from a to b. So in this video, I'm gonna show only the proof of these two properties. So, I'll simply leave the rest of them to you guys to see it, and I think they are quite straightforward to understand. But I'll show you the proof of the next 3 of them in maybe the next video, next 1 or 2 videos. Okay, so let's first get started with the proof of the first property. The function f plus g is integrable. To prove the function f plus g is integrable on AB, still we start from the definition of Riemann integral, right? So, then let's take a look at the definition. So we wanna have that uf plus g minus rf plus g, the upper and the lower integral. The difference of the upper and lower integral of the function f plus g is gonna be, we want to show it's smaller than epsilon, right? And what we know is that we only know f and g are integrable respectively, right? So that is to say, if given a epsilon larger than 0, there must exist a partition P such that partition P on AB such that u f plus g such that we have UFP something, LFP something, and UGP something, LGP something, right? But since we want to relate it to the thing that we want to show, which is UF plus G minus LF plus G, so we write it here and try to expand it to get what we want. U minus L is gonna be smaller than UF plus GP minus LF plus GP, the upper and lower sum of F plus G with respect to the partition P, right? This is I think it's one of the lemmas we talked about before. And so then we want to separate the function f plus g into only f and g, right? So if we can prove that, we have a question mark because we don't know if this is true. If we can prove that we have UFG UF plus GP minus AF plus GP is gonna be smaller than like UFP plus UGP minus AirFP plus AirGP, which is equal to UFP minus AirFP plus UGP minus LGP, right? If we can prove that, then this part is gonna be smaller than, well, say, epsilon over 2, and this part is gonna be smaller than epsilon over 2, right? So then you add them together to get epsilon, right? If we can prove this is true, then naturally we can get that the difference of the upper and lower integral of the function f plus g is going to be smaller than epsilon. And actually we can easily get that this term uf plus gp minus rf plus gp is smaller than these four terms, because, well, I'll explain it here. Suppose we take mk, capital MK, to be the supremum of f plus g x. The supremum of the function f plus g in the interval xk minus 1 to xk with respect to the partition, right? Partition P. And we know that the capital MK is going to be smaller than capital MK G plus capital MK F, right? Because MKG and MKF are supremum of the function G and F at the interval xk minus 1 to xk. It's their MKG and MKF are their supremum at that interval. And if we take the function f plus g, mk is gonna be only smaller or equal to mkg plus mkf, right? Yeah, that's true. And similarly, if we take mk to be infimum of the function f plus g x, where x is in the interval k minus 1 to xk, then we will have mk is larger than or equal to mkg plus mkf, right? For the same reason. So then we will get uf plus gp is smaller than ufp plus ugp, right? Because you are simply taking, because in every small term in every subinterval, the height of the rectangle, right? The height of the rectangle you are taking is smaller. It's smaller than if you separate these two functions f and g apart, right? So the upper sum of f plus g is going to be smaller or equal to the sum of the f sum of f and g respectively, right? So and similarly we will have air f plus gp is larger or equal to airfp plus lgp, right? So then we then have uf plus gp minus air f plus gp is smaller than u of p plus ugp minus fp plus lgp, right? And we finally got that the difference between the upper and the lower integral of the function f plus g is smaller than epsilon. So we prove that the function f plus g is also integrable on AB. But then we also need to show that the integral of f plus g from a to b is equal to the integral of f from a to b plus the integral of g from a to b. And it's not difficult to think about it. It's simply that since we know, I remember I mentioned another theorem before saying that if we know that a function is if a function is integrable, then there must exist a sequence of partition, right? Pn on AB, such that if you take the limit and goes to infinity, if you take the limit of the difference of upper and lower sum of the function with respect to Pn, you will get 0, right? And similarly for the function g, take the limit of difference of its upper and lower sum with respect to Pn, the partition Pn, you will get 0, right? So, and since we also prove that f plus g is integrable, so then we will also have ug plus f plus g, what is the same, minus air f plus g. Pn is gonna go to 0, right? And also, another thing we know from the previous proof, well, is that air fpn plus air gpn is smaller than, well, I'm sorry, the inequality is not from the last, the previous proof is from the lemmas we mentioned before. Air fpn plus air gpn is gonna be smaller than air f plus gpn, right? Well, this part is from the previous proof, right? Okay, and this is gonna be smaller than by lemma uf plus gpn, right? And this is gonna be uf plus gpn is gonna be smaller than ufpn plus ugpn, right? From the okay, so this part is also from the previous proof. Okay, so what we now know is that if we take ufpn minus air fpn plus ugpn minus air gpn, this part will be larger than uf plus gpn minus air f plus gpn, right? And this part is gonna be go to 0. So then, and we also know this part is gonna approaching 0, and this part is also approaching 0, right? So what we then know is that, well, since the by the definition of Riemann integral, right? We define the integral of the function of f plus g from a to b to be the upper and lower integral plus g, which is equal to lower integral of f plus g, right? And similarly, the definition for the function f from a to b is uf, which is equal to lf, and for g is ud, and which is equal to lrg, right? And well then from this part we got u f plus g, right? Which is actually the integral of f plus g from a to b, and from this separate and from these two parts we get the integral of f and g respectively from a to b, right? So we prove the final equation. Okay. So this is the first proof of the first property of the integral, and the second one is actually pretty straightforward, I would say, because when you multiply the function by a real number k, no matter it's like positive or negative, or even it's 0, that doesn't matter, because the only thing that change is the mk and a capital MK and small mk in the in each subinterval, right? And since you actually multiply f by k, so you actually multiply every mk and every like the supremum and infimum by k. So then if the function itself is already integrable, multiplication by a real integral won't change a lot. We can actually write it down, because I feel like simply saying like this is not gonna help. So, well, since we know f is integrable, so this is part 2. F is integrable in AB, and by the definition or theorem that I mentioned before, there must exist a sequence of partition Pn on AB such that limit n goes to infinity, UFPn is equal to the integral of f from a to b is equal to the limit n goes to infinity, LFPn, right? So if k is larger than 0, larger or equal to 0, we have UKFPn is equal to k times UFPn. and AFPN is equal to K times AFPN, right? Because just think about the definition of the upper and lower sum, right? If you are taking, for the same partition Pn, by multiplying k, by multiplying a real number k, the only thing that change is mk and mk, capital Mk and small mk. The supremum and infimum of the function at each subinterval, right? And this is gonna be the same. So the upper sum of kf, the new function kf, is gonna be k times uf, right? I think it's not easy to. I think it's not difficult to imagine that, right? And similarly, air kf, lower sum of kf is gonna be k times the lower sum of f, right?
In this way, we can actually see the lower and upper integral, lower and upper sum are kind of like linear, right? No, that's not true, because if you take UFPN and GPN, UFPN plus UGPN is going to be larger or equal to UF plus GPN, right? So, I'm sorry, the upper and lower sum are not linear. I'm sorry.
Well, let's go back to the proof. Well, up to this point, I think it's very straightforward to get the following. So limit n goes to infinity. Limit u kfpn minus air kfpn is gonna be equal to limit n goes to infinity. Take k out. UFPN minus LFPN, right? And we know that this is gonna be 0, right? So we prove that the new function kf is also integrable, and this part is actually showing that the equation also holds, right? So this is what I want to talk about in this video, and in the next one, probably next 2 videos, we'll continue talking about properties of the integral. So see you in the next one.